Hello, everyone. Yeah, and we're back for another video on differential equations. And this time we're going to talk about families of curves. And you know that this topic follows after the elimination of arbitrary constants. And you know that the solution to an ordinary differential equation contains functions or relations, or set of functions or relations, and those set of functions and relation represent a family of curves. And family of curves, yeah, it's defined as an equation involving a parameter as well as one or both of the coordinates of a point in plane, and they represent again a family of curves. For instance, let us consider this equation. So we have x minus c squared plus y minus c squared equals to c squared. Let us just manipulate this, and this led us to, yeah, that's x squared minus 2xc plus c squared. Then you do the same on the second term. So you have y squared minus 2yc plus c squared equals to c squared. And then combining similar terms, you can write it of the form x squared plus y squared. And then you can group these two terms and you can factor out 2c, leaving you with x plus y here. And then c squared plus c squared, that's 2c squared. And then you can see 2c squared on the right side. Then you can combine the two, then that will become 0. So that leads us to x squared plus y squared minus 2c times the quantity x plus y equals 0. And this equation uh, forms the family of circles whose center lies on the y equals x, on the line y equals x, and passing through the origin. So let us consider those circles. Yeah, and you can see that all the circles has center on the line y equals x and passing through the origin. And there are infinitely many circles that you can draw possessing that characteristics. Now, to determine the differential equation relative to this family of circles, then you can do it by eliminating c. And you can employ the method of elimination of arbitrary constant. And to easily facilitate the elimination of the arbitrary constant c, you can isolate 2c, and that leads you to x squared plus y squared equals 2c times the quantity x plus y. And then you can divide everything by x plus y. And that leads you to 2c equals x squared plus y squared all over x plus y. And then you can now differentiate this. You know that the derivative of 2c is equal to 0. And you can use the derivative of quotient along with the implicit differentiation to differentiate the right side. By employing the derivative of quotient, so you have x plus y in the denominator, you copy x plus y here, and then you differentiate the numerator implicitly, so you have 2x dx plus 2y dy, then minus the numerator, x squared plus y squared, times the derivative of the denominator, which is dx plus dy. Hold on, that's dy. Okay, and then to simplify, you can multiply everything by x plus y to avoid that denominator squared. Sorry, that's x plus y squared, and then you got this. Okay, and then eventually you can use the FOIL method or the distributive property by just distribute x plus y each term here. Okay, and then you do the same here. And then you combine all the terms that will contain dx and all the terms that will contain dy, and that will lead you to this differential equation. And this differential equation represent a family of curves or family of circles with center on the line y equals x and passing through the origin. And to illustrate this families of curves further, let us consider another example. Let us obtain the differential equation of the family of lines passing through the origin. So let us first illustrate it graphically. So we will draw lines that will pass through the origin. And as you can notice, you can draw infinitely many lines that will pass through the origin. And so each line here is represented by the equation y equals mx plus b, or the slope intercept form of a line. And observe that each line here passes through the origin, it means that the y-intercept b is equal to 0. And that simplify our working equation equal to mx. All right? So that's y equals mx. Now, upon considering these lines, then you can notice that the slope of each line varies from one line to another. So this is m1, this is m2, M3 is the slope of line 3, M4 is the slope of N4, and the slopes vary from one line to another. And therefore, we only have one arbitrary constant. You can say that arbitrary constant are variable that changes from different course of the problem. So since we have only one arbitrary constant, then we can just differentiate our working equation once. And differentiating, so you have y prime equals m, or you can just write it in Leibniz notation, dy dx equals m. And you got this. And then what you need to do next is to replace m on our working equation, replace it by dy dx, and that will lead us to y equals dy dx times x. So this is y equals mx. And then multiplying this by dx, yeah. So we'll have y dx equals x dy, and this will eventually lead us to the differential equation that we are looking for. Okay, so y dx equals x dy is also equal to y dx minus x dy equals 0. And this is the differential equation of all the lines passing through the origin. One more. Let us consider the family of lines passing through a fixed point hk. And then this is the point hk. And along this line, you can draw infinitely many lines. And again, we shall use since there is one point. Yeah, there's one point, and then the slopes of each line can be obtained. Then we can use the point slope form of a line. So that's y minus k equals the slope times x minus h. So this is the standard form, or the point slope form of a line. Okay, now let us consider a point here, and then you can draw many lines. The question now is, are these lines member of this family? Okay, so let us consider a point here. Are this line members of this family? So obviously, since from our problem, each line is passing through a fixed point hk, meaning the lines determined from this point is no longer member of this family. Okay, this is another family of lines, and this is also another family of lines. So we are just only referring to, say, this is 4, 5. Okay, so we were only referring to those lines passing through 4, 5. Okay, yeah. So we have y minus k equals m times x minus h. And then you ask yourselves, we have here arbitrary constant m, k or h, and k. Which among this constant are arbitrary? So from the given problem, you say that the lines are passing through a fixed point, which means h and k are fixed, and it means that h and k are not arbitrary constant, meaning it's a fixed constant. So therefore, only m is arbitrary constant. And then we shall differentiate it once. Differentiating, you have y prime, derivative of negative k is 0, you copy m, and you know that the derivative of x is 1. So we have y prime equals m. Or dy dx is equal to m. And then again, you just replace dy dx here to m, and that leads you to this equation. That's y minus k equals dy dx times x minus h. And then you can multiply everything by dx, so that leads you to y minus k dx equals x minus h dy. And eventually, that will lead you to the differential equation y minus k dx minus the quantity x minus h dy equals 0. And this represent the family of lines passing through a fixed point hk. Another one. This time, we're going to talk about the family of circles with center on the x-axis. Okay, so you can let these circles be members of the family we are referring to. Yeah, you can draw infinitely many circles such that those circles has center on the x-axis. Then, yeah. And you can see that if each of this circle has center on the x-axis, say we have here center HK, okay, and this is the radius R. Then we can use the center radius form of a circle written of the form x minus h square plus y minus k squared equals r square, where h and k are the centers and r is the center, sorry, and r is the radius. And since the center is located on the x-axis, and we know that a point on the x-axis, the y-coordinate is always 0. It means that k is equal to 0. So the center is now located at H0. Okay, the next, you can draw the equation of this circle, and that's x minus h squared plus y minus 0 squared equals r squared. And that gives us x minus h squared plus y squared equals r squared. Now, so from the resulting equation, we now only have h and r as our variable. Then you look at the given problem to determine whether h and r are arbitrary constant. The question is if are h and r changing? Because if h and r change from one circle to another, then h and r are arbitrary. Okay? If they are not changing, then it's fixed and it's a fixed constant. So as you can notice here, okay, so we can see that this is your center, H0, and then this is the radius. This is your center. So it probably, I let this to be H1, 0, and this is your another radius, which means the radius R and the H change from one circle to another. And therefore, you can say that H and R are arbitrary constants. So there are two arbitrary constants here, so we shall differentiate this twice. Differentiating, so you have 2 times x minus h plus you differentiate this, that leads you to 2y y prime equals 0. Okay, and then you have, and then you can just introduce to each term inside to easily facilitate the next differentiation. So that's 2x minus 2h plus 2y y prime equals 0. And then differentiating this once more, so you have got 2. You know that the derivative of 2h is 0. Then plus, you employ the derivative of product. You copy 2y, differentiate y prime, plus y prime. Then you differentiate 2y. And that's 2y prime equals 0. And then again, you can now drop 2 off from the equation. So 1, I mean, this will become 1. This will be taken out. Okay. And then that leads you to 1 plus y double prime plus y prime squared equals 0. And eventually, this describes the family of circles with center on the x-axis. That's y double prime plus y prime squared plus 1 equals 0. Say we want to determine the family of all circles. Yeah, the differential equation for all the family of circles. So let's draw some members of the family. Yeah, and even bigger, even smaller. Okay, and then you can notice that R changes from one circle to another. Okay, as well as its center, HK. Okay, and let's just choose one member of the family. Then let's put HK and then the radius. Okay, so since this is a circle with center HK and radius R, then we can use the center radius form of a circle, and that leads you to x minus h squared plus y minus k squared equals r squared. Now, the question is, among h, k, and r, which of those are arbitrary? As you can notice earlier, when I draw circles, the radius changes as well as the center, and therefore we have three arbitrary constant, h, k, and r, because all these variables change from one circle to another, from one member of the family to another member of the family. So we shall differentiate this working equation thrice, right? That's a lot of work to do. Okay, differentiating. So you have 2 x minus h plus 2 y minus k y prime equals 0. And then again, to easily facilitate the derivative, we can just simplify this algebraically by distributing, 2 each term here and 2 y prime each term on y minus k. That leads us to 2x, yeah, 2x minus 2h plus 2y prime, because of the, do not forget this y prime, minus 2k y prime equals 0. All right. Then you can now differentiate this again. So you'll have 2 minus 0 plus employ the derivative of product 2y, y double prime plus y prime times 2y prime. Then minus, you copy 2k, that's constant, and then you differentiate y prime. And that gives you y double prime equals 0. So you have this. And then you can take that 2 off the equation. So you divide everything by 2. All right. And then as you can notice, after the second differentiation, you can still see this k. Okay. There's one more arbitrary constant present on the equation. And again, to easily facilitate the derivative or the differentiation, we can isolate that k. So you shall have 1 plus y double prime plus y prime square, right? Is equal to ky double prime. And then you divide everything by y double prime. All right. So you get this. Then to differentiate, we can use the derivative of quotient. Yeah. So we have 0, the derivative of k, and then you use the derivative of quotient. I will just write a very long vinculum here. And then y double prime square, then you copy y double prime here, and then you differentiate the numerator. Derivative of 1 is 0, plus you use derivative of product to differentiate y double prime. So that's y, then derivative of y double prime is y triple prime, plus y double prime times derivative of y, which is y prime. Then plus the derivative of y prime square by power formula, you bring 2 down here, you copy y prime, then you subtract from 1 from 2, that will become 1, and differentiate y prime. That's y double prime. Close. Minus the numerator, 1 plus y double prime plus y prime square, and then times, sorry for that, derivative of the denominator y double prime. That's y triple prime. Close. All right. And eventually, you have this equation. So to simplify, you can just multiply everything by y double prime square, and eventually you can distribute y double prime each term inside. All right. And then you do the same here. And then do not forget the minus sign. And then let's do it. So eventually, you will only have 0 on the on the left side, sorry. And then this will be canceled out because we multiplied both the left and the right side by y double prime square. And then distributing y double prime, so you have y double prime, y triple prime, yeah, plus y double prime times y double prime, y double prime square times y prime, plus 2y prime, then there's y double prime here, so you have y double prime square. And then you do the same here. Let me just remove this annotation. Then we have y triple prime times 1, then multiply it by negative 1, minus y triple prime minus y triple prime times y double prime is y double prime, y triple prime, yeah, and then minus, then y triple prime times y prime square, y triple prime times y prime square. All right, and then you have this. So I think we can combine, let's see, all right, come on, this term and this term will lead us to 0, so this will become 0, and I think these two terms can be combined, yeah. So you have 0 is 3y double prime square times y prime, all right? And then we just copy negative y triple prime, right? And then this the last term, negative y triple prime times y prime square. And I think this is the differential equation that we're looking for. We just arrange it in decreasing order of derivatives. All right. So you have y triple prime plus y triple prime y prime squared minus 3y double prime squared y prime equals 0. And this is the differential equation of the family of all circles. Another one. All right. Family of circles with fixed radius and tangent to the x-axis. You can see the word fixed. So which means fixed radius, meaning the radius here, which will be represented by r, is a fixed constant, is not arbitrary, right? Because we have the word fixed. Let's draw some circles or some members of the family. So that's hk, and then the radius r. Okay. And since the radius is fixed, then you can say that all circles belonging to this family have the same area because they have the same radius. All right. So these are some of the members of the family of circles, and you can draw infinitely many circles with fixed radius and tangent to the x-axis. Now, again, we shall use, our working equation would have been the center radius form of a circle. That's x minus h squared plus y minus k squared equals r squared. However, okay, we shall identify which of this should be an arbitrary constant. And we can say that r is not arbitrary because, it's fixed radius. However, when we try to, examine the characteristics of the circles, since they are tangent to the x-axis, it follows that the radius is also equal to k, right? Because, say, let's consider this point as, say, let me just say that's 2, 3, okay? So, which means h here is equal to 2, okay, from this point going to to the y-axis is 2, yeah, and k is equal to 3. And since it's touching or tangent to the x-axis, then you can also say that r is also equal to 3, okay? Yeah. So we can say that k is equal to plus or minus r. But why there is a plus minus r there? It's basically because for positive r represent those circles above the x-axis, and negative r represent those circles below the x-axis. So that's why k is equal to plus or minus r. And then we can just replace k here by plus or minus r. And then we got this equation. So we only now have only two variables or two constant, h and r. However, again, the radius r is fixed, r is not arbitrary. Therefore, we only have one variable. Meaning, that tells us that we only need to differentiate our working equation once. And doing it so you just bring this down, yeah? We're just repeating the process earlier. So you bring 2 down, you copy y plus or minus r, and then you subtract 2 from 1. Sorry, you subtract 1 from 2. That's it. Yeah. And then you differentiate y plus or minus r. So that's y prime equals 0. Okay. So we only need to differentiate it once. However, when we try to look at the equation after the first differentiation, all right, we still have an h here, which is an arbitrary constant. So to facilitate the elimination, you can just distribute this to each term inside, or you can just eliminate it, and then you got this x minus h plus y prime y plus or minus r equals 0. So we divide everything by 2. That's why this 2 is missing on the second equation, on the next equation. And then again, to eliminate h, you can just isolate h. So you have h is equal to x. Yeah. So you can just throw this on the other side. So h is equal to x plus y prime times the quantity y plus or minus r. So that is our h. And then the next thing you need to do is to replace h here by x plus y prime y plus or minus r. All right. Then we now have x minus h, where h is represented by this x plus y prime times y plus or minus r, then square, plus, you just copy these terms, y plus or minus r squared equals r squared. And then to simplify, we just distribute this minus 1, each term inside the parentheses. So you'll have x minus y prime times y plus or minus r, and then raise it to the second power. And then copy again the second term, and then the right side of the equation. Oops, that's plus or minus. And then you can combine x and negative x. X, negative x, 0. You only have negative y squared, y plus or minus r square. Oh, hold on. This is y prime, sorry. Oh my. This is y prime. Negative y prime times y plus or minus r quantity square. Plus copy the second term, and then the right side of the equation. And then you have this. All right. Okay. And then the next thing you need to do is to introduce this each term inside the bracket. That leads you to negative y prime square times the quantity y plus or minus r square. Yeah. And then plus y plus or minus r square equals r square. And then simplifying, you have y prime square plus the minus sign here will be eliminated because we are raising it to the second power. Yeah, y plus or minus r square plus y plus minus r square equals r square. And then eventually you have this equation, and then you can just factor out y plus or minus r squared. Y plus or minus r quantity square, then times y prime square plus 1 equals r squared. And this is the differential equation that we are looking for. Y plus or minus r squared times y prime squared plus 1 is equal to r squared, and that's the differential equation for the family of circles with fixed radius and tangent to the x-axis. Let's see some more. Yeah, this time let's talk about the parabola. Let's determine the differential equation for all the parabolas with axis parallel to the x-axis and with the distance from focus to vertex fixed as a. Let's illustrate it graphically. So we are referring to, the keyword here is axis parallel to the x-axis. That means our parabola opens right or left. Since, yeah, all right. Since the parabola has axis parallel to the x-axis or horizontal axis, and that's the axis of symmetry of the parabola. Okay, let us choose a representative member of the family, and that's the parabola, and this is the focus. Yeah, and the distance from the focus to the vertex HK is fixed at A, which means all all the members of the family has the same distance from the focus to the vertex, and which means they have similar span. They will only differ on their opening and their vertices. Okay, which means the vertices HK or the vertex HK is an arbitrary constant. H and K are arbitrary constant, and where A is not arbitrary. It's a fixed constant. Okay? And then we shall use the standard equation of a parabola with horizontal axis of the form y minus k squared equals plus or minus 4a times x minus h. Okay? All right, that's our working equation. And the positive here are for all those parabolas opening to the right, and the minus here are for those parabolas opening to the left. And then we can say that the h and k are arbitrary constant, a is fixed. And then we shall differentiate this twice. Differentiating, you will have 2 times y minus k, y prime, equals plus or minus 4a. And then you know that the derivative of x is 1 and derivative of h is 0. So you will get this. Then you can divide everything by 2. No, to make this a little simpler. All right. So you have y minus k y prime equals plus or minus 2a. And then since we need to differentiate this once more, we have because we have two arbitrary constant, and then you can isolate k, okay? Since a is constant, so you can isolate k to make the differentiation a lot easier. So you have y prime minus k y prime, all right, equals plus or minus 2a. Differentiating again, we shall have you can use the derivative of product here. So you'll have you can isolate k to make to make the derivative a lot easier. So you shall have k equals y plus or minus 2a over y prime. Okay, that is our k. And then you can now differentiate derivative of k, 0. Derivative of y is y prime plus or minus. And then to differentiate 2a over y prime, you can, you can put this on the numerator. So that's 2a, or you can use derivative of quotient. But let me just put it on the numerator. Y prime raised to negative 1 equals, by power formula, negative 1, bring it down, 2a, you copy y prime, then you subtract 1 from negative 1. So that will become negative 2. And then differentiate y prime, that will lead you to y double prime. Or this is negative 2a y double prime all over y prime quantity square. And eventually you will have this equation. All right. And then you can just multiply everything by y prime square. So that will lead you to 0 equals, all right, y prime times y prime square will become y prime cube, then plus or minus 2a, and then you just copy y double prime. And I think this is the differential equation that we are looking for. All right, so that's y prime cube plus or minus 2a y double prime equals 0. And I think that's it. That's the end. And I hope you were able to learn something new from our discussion. All right, let me just delete this one. Hold on.